There are these hidden forces that literally speed up our world. It's a fundamental process that's happening all around us. And yeah, even inside of us, that makes pretty much all of modern life possible. It's called catalysis, and it's like this unseen engine that drives everything from the food we eat to the fuel in our cars. So let's dive in. To really get a grip on just how powerful this is, let me ask you a question. What's the one scientific process that's responsible for both feeding billions of people and, at the exact same time, for providing the raw materials for some of history's most devastating weapons? The answer, well, it shows you the incredible and kind of terrifying double-edged nature of science. The story really starts with this number, 4.3. That's how many people we can feed today for every single hectare of farmable land. Now, back in 1908, that number was just 1.9. I mean, that is a massive leap in our ability to grow food, and it's almost entirely thanks to the invention of synthetic fertilizers, all made possible by one world-changing chemical reaction. And here's where things get complicated. The process that makes this all happen, the Haber-Bosch process, is the absolute cornerstone of modern agriculture. It synthesizes ammonia for fertilizers. But that very same ammonia is also a key ingredient for making explosives. So it's a lifesaver and a destroyer, born from the exact same science. This brings us to the man behind it all, a figure who perfectly captures this conflict between creation and, well, destruction.
So meet Fritz Haber. In the early 20th century, he solved one of humanity's biggest problems: how to get nitrogen. See, our air is packed with nitrogen, but for plants, it's totally useless, like being locked out of a pantry full of food. Haber figured out how to pull that nitrogen right out of the air and turn it into ammonia, completely changing fertilizer production forever, and for that, he won a Nobel Prize. But his story has a very dark side. When World War I broke out, Haber took his genius and applied it to the German war effort, saying it was his patriotic duty. He became one of the key figures in chemical warfare, leading the development of poison gases used in the trenches.
So you've got this incredible legacy, right? But it's completely split down the middle. On one hand, he helps feed the world. On the other, he enables destruction on a massive scale. But how did he do it? The reaction to make ammonia was known, but it was just ridiculously slow. The secret, the thing that made it all work on an industrial scale, was a catalyst.
And this takes us from all that historical drama to the core science. We've seen what catalysis can do, but what exactly is it? What's going on under the hood? So here's the classic definition. A catalyst is basically a chemical matchmaker. It jumps into a reaction, makes things happen way, way faster, but then it pops out at the end completely unchanged, ready to go again. Now, a catalyst doesn't actually change the final outcome of a reaction. It's not magic. It doesn't make more stuff. Instead, think of it this way. A catalyst doesn't change where you're going. It just builds a super highway to get you there in a fraction of the time. It's all about providing a shortcut. And to really get that shortcut idea, let's use a super simple but really powerful analogy: the mountain and the tunnel. Okay, so every chemical reaction has something called an activation energy. Just imagine it as this huge mountain that your starting chemicals, the reactants, have to climb before they can roll down the other side and become products. And it takes a ton of energy to get over the top. Without a catalyst, that mountain can be almost impossibly high. For that ammonia reaction, at room temperature, it's so high that the reaction would basically never happen. I mean, not in our lifetime. That's the huge energy barrier you see here. But then you add a catalyst, and look what happens. The energy you need just plummets. That massive mountain, it's like it shrunk. But the catalyst hasn't actually moved the mountain. It's done something much, much smarter. It builds a tunnel. It creates a brand new, easier path for the reaction to take, one with a much lower climb. This is the secret to its speed. It just makes that journey from A to B so much easier and faster. And this whole tunnel building idea, it's not just some weird thing for industrial chemistry. No, it is happening all around you right now. For instance, think about the catalytic converter in your car. It uses solid metals like platinum to turn really nasty exhaust gases into much safer stuff like carbon dioxide and water. This is a perfect example of what's called heterogeneous catalysis, which just means the catalyst, the solid metal, is in a different physical state than the reactants, the exhaust gases. So what's actually happening in there? Well, first, the harmful gas molecules literally stick to the metal surface. That's adsorption. This grip weakens their chemical bonds. Then, while they're stuck there, they react and rearrange into safer molecules. and finally, they pop off, leaving the surface clear for the next batch of exhaust to come through.
But catalysts aren't always the good guys. Up in our atmosphere, we see the other side of the coin, homogeneous catalysis. This is where the catalyst and the reactants are all in the same state. In this case, they're all just gases floating around together.
And this is what's so scary. Scientists figured out that a single chlorine atom, knocked loose from a CFC molecule by sunlight, acts as a catalyst to destroy ozone. And because that chlorine atom is spit back out at the end of the reaction unchanged, it can go on a rampage, destroying thousands and thousands of ozone molecules. It's why CFCs were so incredibly bad for the ozone layer.
Okay, so we've gone from factories to cars to the sky above us. Now let's bring it right back down to the most personal scale imaginable, the catalysts that are working inside your body right now. We call them enzymes. So how do these little biological machines work? Well, for a long time, we thought of it like a lock and key. The enzyme had a perfectly shaped slot for its target molecule. But a more current idea is the induced fit model. It suggests the enzyme is actually a bit flexible, and it changes its shape to get a perfect grip on its target, kind of like a handshake.
And the variety of these things is just mind-blowing. They're all sorted into different classes based on what they do. You've got hydrolysis, which use water to help break down your food, while isomerases just shuffle atoms around inside a molecule. I mean, there's a specialized enzyme for almost every single chemical reaction that keeps you alive. They're the real accelerators of life itself.
So you see, from feeding the planet, to threatening our atmosphere, to literally powering our own cells, catalysts are these fundamental accelerators. They are a tool of immense power, and if the story of Fritz Haber teaches us anything, it's that with that kind of power comes huge responsibility. So the final question isn't just about chemistry, it's about our future. What reactions do we as a society choose to speed up next?